So looking at page 54 in the Unit 3 packet, we're going to talk about the different ways in which the central limit theorem works its way into normal distribution type questions. So the first question here is actually not, well, it is a normal distribution. It's not a central limit theorem question. The second one, very similar, but it is central limit theorem. And at first glance, you can see a subtle difference, but then you can see an obvious difference. All right, so number one, it says find the probability that the score, whatever the score is above 140, given that the mean is 143 and the standard deviation is 29. All right, so we would find the z-score of 140, which would be 140 minus 143 over 29. Just get rid of some of this stuff. All stuff from the last video. And let me close this down. Okay. So what I wanted to do up here. All right, so for the Z max, that's going to be something big. All right, so I'll put it in as like 10, whatever. It doesn't make a difference at this point. We can adjust the slider as we go. But 140, 143, oops, too many threes. And we're looking at about negative 0.103. All right, so that's going to be a smidge to the left of the vertical axis. Make it look more like a smidge, and we're looking at area to the right of that. All right, so z of 140, we know it's going up to infinity. The probability that z is going to be more than negative 0.103 is approximately, I got to scroll down. Oh, I've got too many little fields there. All right, now I got to just verify that it's actually that the probability is going to lock in the way it ought to. So as I scroll from left to right, you see it's picking up at negative 0.103, and as I go to the right, fluctuation in my normal distribution calculation, my probability calculation, until it converges on the appropriate number, which is about 0.541. All right, so that's the probability that this score is above 140. All right, now what I need is the probability for number two that the mean score is above 140. All right, the mean score, that's the subtle little add-on here. Given that the mean and standard deviation are 143 and 29, and that n is now 100, all right? So that's the other subtle little difference, right? Well, actually, it's less subtle. It's pretty overt, but if you're not looking for it, you might miss it, all right? So we're looking for the z-score corresponding with the 140, but this time, instead of it being an x value that's above 140, we're really looking for the probability that x bar is above 140. So the formula that we would use, and actually I'll come back to this in a second, the z-score formula that we would use is z equals, instead of x, x bar, instead of mu, mu sub x bar, and instead of sigma, sigma sub x bar. All right, now the good news is, based off of what we learned on the previous page, x bar we're stuck with, but mu sub x bar and mu are the same thing. Sigma sub x bar is the same as sigma over the square root of n. So when I want to find z sub 140, it's a matter of saying, okay, I got my 140, I got my 143 over 29 over the square root of 100. All right, now that you just type in. All right, so on the low bound, I mean, there's really not much to change except to make it over the square root of 100. The z-score for for the minimum is negative 1.034 blah, blah, blah. Which is going to put it somewhere in this neighborhood. We're still looking for the area to the right, but we're now looking for the area to the right of a different value. We're looking for the area to the right of a value that's more to the left. So we're going to get a probability that's larger. All right, so if we scroll down, just verify that our slider is going to lock us in the way it ought to. All right, as I scroll up, you can see fluctuation, but then once I get closer and closer to 10, it locks in to about 0.850 if we go to 3 significant. All right, so we have about a 30-point jump in probability. All right, substantial. And it has to do with the central limit theorem in the sense that whenever you find the mean of a sample, what you're doing is you're reducing variation substantially. All right, so you're getting rid of all the extreme values. The mean is very sensitive to extreme values, but if you take the mean of a set of means, it'll centralize the data set, but it'll also minimize the impact of extreme values within any individual data set, right? Any individual sample, I should say. All right, so when we looked at each one of these samples here, each one of these samples had one, like there was a 1, there was a 4. You might look at the 4 as an extreme value. You might look at the 1 as an extreme value, but let's just focus on the 4. All right, so by pairing the 4 with a 1, so looking at this one here, pairing the 4 with the 1, we negated the impact of both the 1 and the 4. All right, that was actually the 4th entry. You'll notice how that became, let me circle that actually. The 1 and the 4 in the what we call the sampling distribution became a 2.5. All right, so we lost the impact of the extreme values 1 and 4, and it got centralized to a 2.5. All right, the only instance in which the 4 remained as part of the sample is when both individuals that made up the sample were 4. All right, so what's happening is the power of the number 4 was lessened by being part of this sampling distribution. All right, and so that decreases the variation. That's why we were looking at something that went from a 1.118 to a 0.791. All right, and so it's always going to be reduced based off of the fact that it's being put into individual samples and means are being taken. All right, so that's what's happening here, is that, and we don't have any context, so it's kind of hard to really capture the idea, but you got to imagine that if 143 represented a score, let's say it's a score on some test that's like out of 200, or it could be blood pressure. Maybe individuals who have high blood pressure. Actually, let's go with that. You got to imagine that in this group that's been sampled, let's say that there were 10,000 people that were sampled from a population. Well, actually, it says mu is equal to 143, so it's actually the population. So somehow they got a hold of all the people in the world who had hypertension, or whatever they were defining as a population. I want to be realistic about it. And they determined that the mean was 143 for that population that they defined. You got to imagine that in that population there were going to be some extreme values. Like there had to be somebody who had like 170 as their top. I'm assuming that this is the diastolic is the top number, systolic. Well, one of them's the top number. All right. So we're gonna, because if it was the bottom number, then that's a different story. All right. They wouldn't be conducting a test on these individuals. They'd be admitted to the hospital. But the reality is that there had to be an individual whose blood pressure was really, really high, But because of the sampling distribution, that high value was centralized to something much lower. All right. So because there is a smaller standard deviation for your sampling distribution, you end up with more significance to any movement along the z-score scale, the horizontal line that makes up your normal distribution. So the further you are away from the mean, the more impact that has, because that's covering more ground probability-wise. All right. So number 3 actually adds a little context. Math professors have IQs that are normally distributed with a mean of 125 and standard deviation of 1.2. If one math professor, so you see it's not normal distribution, I keep saying that, not central limit theorem, because it's one math professor being selected at random. Find the probability that his IQ is greater than 127. I went with his because I was talking about myself. All right, so probability that x is greater than 127. We would want the z-score for 127, which would be 127 minus the mean of 125 over the standard deviation of 1.2. All right, so let me just get rid of all this. Minus 125. You can just write a 2 if you want. So about 1 2/3. So I'll write it as 1.6 repeated. So 1.6 repeated is going to be somewhere in this neighborhood. That's what we're looking for. So the probability that that individual is going to have an IQ greater than 127 corresponds to the z-score being more than 1.6 repeated. So again, we scroll with our scroller, and we keep scrolling to the right. So I'll start off at like 1. You see, or in the neighborhood of 1, because we've got to get better than 1.7 roughly. But you can see it's shading in more. It's not purple anymore. It's just, it was only purple because the red and the blue overlaying its primary, secondary colors. Anyway, so as I scroll to the right, you can see the probabilities are converging on what it really is, and it locked in at about 0.0478. All right, so a little bit less than a 5% chance that if you select a person at random, that their IQ is going to be better than 127, assuming that all the IQs are distributed with a mean of 125 and a standard deviation of 1.2. Now, to get a cluster or a group of 75 individuals, all right, so now n is 75. We want to have mean IQ greater than 127. So that's asking us to take or find the probability that x bar is greater than 127 for these individuals. So the z corresponding with 127 would now be 127 minus 125 over the sigma value, which was 1.2, but now divided by the square root of 75. All right, so this is the mu sub x bar, and this whole thing is the sigma sub x bar. All right, so we crunch that, minor adjustment here, divided by the square root of 75, and we're talking about a minimum z value of 14.434. Yeesh. I don't even think I could draw that on the graph, because 14, I mean, this only goes out to 3. Here's 1, 2, 3. It's off the graph. All right. So when I want to try to come up with the probability here, I get an error on my normal distribution. That's because my z max isn't big enough. So that I can do. I can change that to like a 20. And then just do some scrolling here. You got to get up to about 17 or 18 before it locks into place. it converges on the appropriate value. But once it does, we get the probability that the z-score is greater than 14.434 approximately. It's going to be 1.587 times 10 to the negative 47th power. All right, that would be like writing point and then writing the number 0 46 times and then starting with the 1587. All right, that's obnoxiously small. It's to the point of almost being impossible. So what does that mean? Well, it means a couple of things. The most important thing is that it's very, 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 very unlikely that you're going to find a group of 75 math professors whose average IQ is more than 127. There's a small probability that you'll find an individual, and that was 5%. There's a small chance that you'll find an individual that was at this particular level of IQ, but having a group of 75, that's almost to the point of being impossible. Now think of it in the context of, like your own experience with teachers. Forget about math, just all of your teachers. If you were to take and actually don't even think about the numbers, just think about good or bad, right? So just contextualize it in your mind as they're either good or bad. If I told you or I asked you what's the chance that out of all the teachers that you've had that you could identify just one who was good, you'd say probably a high probability. Then if I were to follow that up by saying, can you name 75 of your teachers that were in the category of good? What are the chances of that happening? I would say probably less so, because you had to have a couple of stinkers in there. So maybe I'm one of them. I hope not, but maybe that's the case. So it's possible that, or very, very likely that you've had a teacher that you'd say, oh, that was a good one. So I can easily name the good teacher. Name 75 of them. Oh, I don't think I can do that. Right? That's really what we're getting at here. That's what the central limit